All right, guys. So in this one, we're going to talk about something called trapezoidal sums or the trap rule. So if a function is integrable on a closed interval, then for any partition a to b and n subintervals, the definite integral is equal to. Now, you don't have to memorize this, but here's the key right here. It's essentially the average of the left and right sums. Okay. So let's do an example to kind of solidify this. We want to approximate the definite integral from 1 to 5 of e to x over x using trap sums. In this case, we're going to do four subintervals. Okay, so we're going to go from 1 to 5 right here. We have our four subintervals. A trap rule would essentially superimpose trapezoids by connecting the left and right endpoints with a diagonal line. Now you can see that this trap rule is going to over approximate it, but it's really close to the graph, to the true value of the definite integral here. Okay, so we partition into four subintervals. So delta x is going to be 5 minus 1 over 4, which is 4 over 4, which is 1. So we already drew that. Now we're going to get the value corresponding to each of those endpoints. So f of 1 equals e, f of 2 equals e squared over 2, f of 3 equals e cubed over 3, f of 4 equals e to the fourth over 4, and f of 5 equals e to the fifth over 5. All right, we're going to need those values to keep going. And notice I'm using exact values because this isn't a final answer yet. So if I want the left Riemann sum, okay, I'm going to use the left endpoints for the four rectangles and then multiply it by the width. So that's going to be e plus e squared over 2 plus e cubed over 3 plus e to the fourth over 4. All of those are going to be multiplied by 1, and that's going to be approximately 26.75752. For the right, I'm going to use now no longer the left endpoints. Okay, I'm going to use the right endpoints. I guess I could have used L's there. So the first subinterval goes from 1 to 2. The right endpoint is at 2, so that's going to be e squared over 2. The next right endpoint is e cubed over 3. The next endpoint is 4, so e to the fourth over 4, and then e to the fifth over 5. All of those multiplied by 1, which is the width. So that's going to be approximately 53.72187. All right. And then our approximation here is going to be the average of those two. So 1/2 times 26.75752 plus 53.72187, which is 40.240. Now, if you do have to get decimal values because you're using a calculator or Desmos or something like that, make sure you go out as many decimal places as you can until you get to your final answer, and then you can write it there. So something to notice in this case is that I could very easily see that the trap method is going to over approximate this function because the tops of the trapezoid stick out over top of the graph. And the reason is because the function is concave up. So here's a couple things. Um, if the second derivative is positive on an interval, then the graph is concave up, and then the trap sum is going to overestimate. And you could just very easily draw a concave up graph, put a couple approximating intervals in there, and then connect the tops of them and see that it's going to over approximate. If the function's concave down, doesn't matter if it's increasing or decreasing, we draw a couple approximating intervals and then connect the tops of them to see that the trapezoid rule is going to under approximate it, leaving some gaps. Now here's an additional tidbit. The midpoint rule is always going to give the opposite kind of approximation that the trap rule does. So if the trap rule over approximates, the midpoint rule is going to under approximate it. Okay? All right, one final example here. We're going to approximate the natural log or the definite integral of the natural log from 1 to 3 decimal places with 4 subintervals. And then we're going to show you how to do this on the calculator to get the final answer. So if we're going from 1 to 3, this is the region that we're going to do. Now we want to do left Riemann sum. We're doing 4 subintervals. So delta x is b minus a over 4, which is 1/2. So each subinterval is half a unit wide. So for the first one, it's going to be f of 1 times 1/2 plus f of 2, or excuse me, 1.5. Let me just fix that up right there. F of 1.5 times 1/2 plus f of 2 times 1/2 plus f of 2.5 times 1/2. All right, and then we'd have 1/2 times those function values for all of those there. So f of 1 is 0. F of 1.5 is natural log 1.5. And then f of 2 is natural log 2. And then f of 2.5 is natural log of 2.5. Okay. And then if we add all that up, multiply by 1/2, you get 1.00745. Okay. Now, if we want to do, so that's part A, that was left. Part B is the right. Delta x is still going to be 1/2. Okay. But notice if we use the right endpoints, it's the 3 of them are the same, the 1.5, the 2, and the 2.5, but then we're going to use 3. So it's going to be 1/2 f of 1.5 plus f of 2 plus f of 2.5 plus f of 3. So that's 1/2 times natural log 1.5 plus natural log 2 plus natural log of 2.5 plus natural log of 3. So you add all of those up and multiply by 1/2, and you're going to get 1.55676. Now, a couple things here. These two answers, we could report them accurate to 3 decimal places for the AP exam. So 1.007 and 1.557 would be sufficient. To do the trap rule, we're going to add those up and divide by 2. We would not want to use our rounded 3 decimal place answer to add those up and then divide by 2. We're going to use the longest decimal form that we have. So by the trap rule, we're going to have for part C, the integral from 1 to 3 of natural log x dx is going to equal 1/2 of 1.00745 plus 1.55676, which is approximately 1.282. Okay. Now, the left Riemann sum, if I just take one approximating interval, the left Riemann sum is going to under approximate it. If I do that same interval and I use the right endpoint, you can see that the rectangle for the right endpoint would stick out over, so it's going to over approximate it. And since the function's increasing and concave down on the whole interval, I know that all the rectangles for the left are going to under approximate and all the rectangles for the right are going to over approximate. Now, since this function's concave down, the trap rule is going to under approximate it here, because you can see that a trapezoid is going to be very small, but it's going to be below. There's going to be a little bit of a gap. So this is going to under approximate it, but the approximation is going to be much, much closer with four subintervals for the trap method than it is for the left for this one here. Okay, so this brings us to the last part here where we're actually going to do this on the calculator to get the calculator to approximate it. So we'll turn the calculator on, hit math, and then we scroll down, I believe it's number 9, integrals, so number 9. And then we put the function in, natural log x, comma x, comma 1, comma 3. All right. If you have a newer calculator, it's probably going to prompt you with the actual integral symbol, and it'll be much easier and more intuitive. So 1.295 there for that one, or 1.296 is the exact answer for that one there. Okay. I'll show you also how to do this quickly on Desmos. Okay, so we had f of x equals natural log x. If you type in int, that's going to give you the definite integral symbol. You have 1, 3, and then just hit over once and put ln x, and then type in dx, and it gives it to you. If you have the function defined previously, you can do int, then 1, 3. I'm not sure if f of x dx, yeah, it's going to work because we already named what f of x is right here. Now, it doesn't graph the area under the curve or anything like that, but you can still get the answer. And notice we got the same thing there as we did on the calculator of 1.2958. Okay. All right. So I believe that is the end of the section for us. So hope that was helpful to you. And you guys can reach out if you have any questions. Take care.